Well, welcome to Yuan Gao's thesis defense. Yuan's been around for quite a while, and for the past few years, he's actually been working down in San Jose, and this created a little bit of a lacuna in his ability to finish the degree. But Yuan worked on generalized matrix-fractional functions, and there's many applications all over the matrix optimization literature. He'll be discussing a few of them. And this work is devoted mostly to understanding the underlying convex geometry and convex analysis and duality theory for this class of functions and its relationship to applications. So, Yuan, why don't you take it away?
So, can you guys see my screen? I'm sharing.
Yes.
Let me make it full screen. Okay, so thanks, Jim, for the introduction, and thanks everyone for coming. So I'm going to talk about this generalized matrix fraction functions and their applications. So it's mostly joint work with my advisor, Jim Burke, and our collaborator, Tim Hoheisel, who is now in McGill University. So the idea of this concept of generalized matrix fractional functions was introduced back in 2015 by Burke and Hoheisel. And we have done a bunch of follow-up work on top of that, which is what I'm going to be discussing today. Just briefly to interrupt me with any questions. We also have questions at the end of the talk. Just an overview of the talk. I'm going to first introduce you to this object. We abbreviate as GMFs. So I will present some existing results and some motivating applications. So GMFs appear in a wide range of applications. Also, throughout this talk, I will try to spend more time on applications. So I think that is where most of the guys will be interested in. In the second part, I'm going to talk about convex geometry of GMFs. Based on that, we study the infimal projections. So that is also where most of the applications arise. So finally, I will give some concluding remarks and some exciting future directions that you can work on. So first of all, let's look at this quadratic optimization problem. So we are maximizing a quadratic in Rn, and we denote this gamma xv as the optimal value function for this problem. What that means is that I'm looking at, as we change the problem parameters x and v, how does the optimal value changes? So this function reflects that. It is shown in Burke and Hoheisel's paper in 2015 that this gamma function is actually equals to what we call the pseudo-matrix fractional function. So the V dagger here means the pseudo inverse of the matrix. It's basically a generalization of the inverse when the matrix is not invertible. It's also shown that it is the closure or the lower semi-continuous Hall, which I'm going to explain in the next slide, of the well-known matrix fractional function. So this is the matrix fractional function. I guess maybe a lot of you guys already know that. It's especially if you have studied convex analysis or convex optimization before. It appears in a lot of textbooks as an exercise to ask you to show that this function is jointly convex in X and V. So in fact, if we restrict our attention for this optimization problem to only focus on the case where V is positive definite, we get the optimal value function is the matrix fractional function. Okay, so to introduce the closure, I'm going to first introduce a concept called epigraph. So the epigraph of a function that is defined from a Euclidean space to R bar. So the R bar here is, we call it extended reals. So it's basically augment the real numbers with plus infinity, which is very convenient tool in optimization. So the epigraph is defined in a lifted space. So it's the product space between the Euclidean space and R. So essentially it just represents everything that is above the graph of the function f. So a picture example is like this. So suppose I have a function that looks like this. Doesn't have to be continuous. So the epigraph is just everything above this graph. So the nice thing about the epigraph of a function is that a lot of the properties of the function itself translates to the property of the set. This epigraph of f is a set. So for example, a function is convex or closed if and only if the EPF is closed or is convex or closed. So take this picture example. So the function is definitely not convex because the epigraph is not a convex set. And the epigraph is a closed. So that means that the function is a closed function. So the reason is that, so for this function, since at the point of discontinuity, I'm defining this point, the function value to be the lowest value here. And so when you look at the definition of the epigraph, it includes everything above. So the vertical line here is included in the epigraph. So that's why it's closed. So I suppose, for example, if we define the function value to be up here, then the epigraph will no longer be a closed set, right? Because this part will be open. But in that case, if you take the closure, what we mean by the closure of the set is that we first, if the epigraph is not a closed set, we take the closure of that set and the corresponding function, we call it the closure of the function. So the next important concept I'm going to introduce is support functions. So one of the reasons is that support function is so useful in convex analysis. Perhaps more importantly, later we will show that all these GMFs we are going to study are support functions. So if you give me a set S in the Euclidean space, so the support function of the set is defined as follows. So for any given point X, I look through all these points in the set S, and I'm looking for the maximum inner product. But it's clear that this function is positively homogeneous, meaning that if you multiply X by a positive scalar, you get a lambda for lambda X, and then you get lambda times the output. For that reason, it might be interesting to just look at the case when X is a unit vector. So in that case, it gives us a direction. But what this support function tells us is actually the distance from the origin to the supporting hyperplane of S given by that direction, because normal vector is that direction. So a picture example is this. Suppose I have, this is a closed and convex set. So the X is given in this direction. I have the supporting hyperplane. So the red part is what the support function gives us. So it's the distance. So we can also write this set S itself in terms of support functions. So what this equation means is that for a closed and convex set, so the set itself could be written as intersection of its supporting half spaces. So this also established a very nice isometry between closed and convex sets and support functions. So that's why the support function is such a useful tool in analysis to study the geometry of convex sets. But in the case when the set is non-convex, for example, I'm showing an example on the right. When the set is open or non-convex, we can still do the same thing. We can still look at the intersection of its supporting half spaces. What we get is not the set itself, but its closed and convex Hall. So in that sense, the support function is blind to this non-convexity. And that means we also have the support function of a set is equal to the support function of its closed and convex Hall. So now back to our example, we are looking at this pseudomatrix fractional function. Remember that it is the optimal value function for the quadratic optimization problem. So now we can see that it is actually a support function of the following set. So take a very simple example in R2, for example. We have, this is essentially the graph of a parabola heading downwards. Right? The set itself is definitely not convex in R2, but we can take the convex Hall. The convex Hall of that is simply the hypograph. By hypograph, I mean the opposite of epigraph. It's all the things that is underneath or beneath this graph. So we can look at the support function of the set, which is also the support function of the hypergraph, just by plugging in the definition, right? It's the support function is the supremum of the supremum of the inner product between these sets. But because this is defined in a product space, so the inner product, we define it as the inner product between XU plus the inner product between V and this second term. So which exactly recovers the quadratic optimization problem, right? So we see it is a support function. So what we call this generalized matrix fractional functions. It's again a support function, but we expand this underlying set. So we generalize it so that it includes all matrix valued quadratic mappings. Also, we add in an affine constraint. For example, at the absence of affine constraints, when a and b equals 0, we just generalize this gamma function to matrix variables. In that case, we have a matrix X here. It becomes the trace of X transpose V dagger X. And with these added affine constraints, so the things becomes a little bit more complicated. So in 2015, Burke and Hoheisel in their paper, they showed the explicit form for the GMF. You can still sort of see the shape in there, but instead of V dagger, we replace it by the MV, which is defined here. So this matrix is actually pretty well known. It's studied in a lot of places. It's called the bordered Gramian matrix. And we basically know how to compute a pseudo inverse. We also know under which condition this function is invertible. And so in the following of the talk, I'm going to use this var phi xv to denote this GMF functions. I mean, because this support function is a little bit cumbersome to write. And especially when the A and B is clear from context, I will just use var phi xv to represent the GMF functions. To give you some, instead of showing you the whole proof of this, I'm just to give you some sense, example to see where this MV come from. So if we look at this, again, the quadratic problem, but now I add in an affine constraint. So I'm also writing this, the previous, I'm writing as a maximum, I'm writing now as an infimum, but I'm putting a minus sign in the front. Right? And to solve this problem, we write down this Lagrangian, and we write down the first order optimality conditions, which is equivalent to solving this following system of equations. And you see that this is where the MV comes from, right? And you can, so to get the optimal U and lambda, the Lagrangian multiplier, you need to have MV dagger times X and B, and you plug it back in, then you get something similar to this form. All right, so now let me move on to applications. So there's so many applications for GMFs. So I think in my talk, I'm going to focus on applications in machine learning because that is personally what I'm interested in. And also machine learning is a really hot topic in recent years. Oh, by recent, I mean past 10 to 15 years. It's, so the first example we are going to look at is k-means clustering. So the idea is that if you give me, we have n data points in RM. So I organize it in the data matrix. So each row of the big matrix X is a data point. So the idea of k-means is that I want to cluster the points into k clusters so that the total distance from the points to the cluster centers are minimized. So this can be expressed as an optimization problem in this form, where we have the matrix C represents the k cluster centers. It's a k by m matrix. So each row of it represents a cluster center. And the E is a cluster assignment matrix. So each is n by k matrix. So each row of E is one of the canonical bases in RK. So it just assigns one of the clusters to the corresponding row in X. Right? So the so-called k-means algorithm usually works in an alternating minimization manner. Right? So it's first, suppose I have the cluster assignments, it's easy to find the optimal cluster centers. And then given the cluster centers, I redo the assignment and so forth. And this process iterates into convergence. So this process could also be represented algebraically. Right? For example, if I'm given this cluster assignment E, I can solve this problem. It has an explicit form for the cluster center C. Right? So now if I plug in the C back into this objective, the thing in the front of X becomes this matrix P. It's not difficult to see that the P is symmetric. And also, if we apply P again, we get back to P itself. So P is an orthogonal projection, which also means that I minus P is also an orthogonal projection. And using that, we can rewrite the objective in this form. Remember that our GMF function looks like the trace of X transpose V dagger X. You see now we recover, we see this is actually a GMF function. And through the study of GMF function, you'll see later that we can give some guarantees because we know that the k-means is a non-convex problem, right? We don't have any guarantees in the algorithm, but we can have some guarantees on the object optimal value for this function. So the next example I'm going to talk about is multitask learning. So we have T task, right? Each task is represented by a bunch of training data points. We have X and their corresponding labels. So the prior assumption about in the multitask learning is that we think that this set of tasks are somewhat related. So we could, so how do we encode this information is that we define a linear feature map that maps the original features to a feature space. And then all these predictors for each task is just a linear predictor based on these transformed features. Right? So the cool part is about the multitask learning is that we are trying to learn this feature map as well as the coefficients for each task simultaneously, jointly, right? So we can write down the objective as, so the first part is a usual loss function, and second part is a range like regularization for each task. So the 2-1 norm is basically just the sum of the Euclidean norms for each column, which we are just imposing a range like regularization for each of the tasks. So now if we denote the matrix W as the multiplication of these two matrices, which is the matrix that's governing the feature map and the matrix for the coefficients for each task, then it is shown by the paper by Agrio and their collaborators in 2006 that this non-convex problem can be written or is equivalent to the following convex problem, where again we see the GMF function appears. So using the later results in this paper, we can see that this is actually equivalent to a nuclear norm regularized problem in terms of W. So the nuclear norm is sum of the singular values of the matrix is usually used as a sparsity inducing penalty in machine learning. Okay, so the next problem is about support vector machines. This is perhaps more widely known. We call it SVMs. It's used as a classification problem. And the idea is that suppose I have two classes of points, and we say that these two classes of points are called linearly separable if I can find like two parallel hyperplanes that can separate these 2 points, right? The point of SVM is that we want to maximize the margin between these two hyperplanes so that we have, so the points that lie on these hyperplanes are called the support vectors. And of course, sometimes like these two classes of points are not linearly separable. That is what's mostly likely to happen in practice. So we can relax the constraint. So to allow the point to lie within the margin or even beyond the margin, depending on whether we choose this beta to be greater than or smaller than -1. So for SVM, we can write down the optimization problem like this. And it's usually people solve this using the duals. We can write down the dual problem that looks like this. Again, we can show that the dual objective, the optimal value function for the dual, can be written as a GMF. So in that case, we can provide some insight into the optimal value for support vector machines after we study GMF. All right, so a somewhat related example is supervised representation learning. So that you see that again, it's about a classification task. So in SVMs, if you look at the dual formulation, so you see the whole problem only depends on inner product between the data points, right? So that's why people usually apply this so-called kernel trick. So you map the original data points to a feature space, and then because the whole problem only depends on the kernel matrix. So the thing about representation learning is that suppose we have a set of candidate kernels and we want to select what is the best kernel for this problem. So one way to do this is that we can maximize the alignment of the kernel with the training labels. That's one way to do it. Another way to learn kernels is to start from the dual formulation of the SVM and we do a minimax optimization, right? We minimize the objective among all the possible candidate kernels. So in that case, we see this GMF function appears again. But in this case, it is an example where we have a linear constraint. In this case, we have the A equals to Y transpose and B equals to 0. Actually, the case, the B equals 0 is pretty important because in that case, this GMF function is not only a support function, but we also show that it is a gauge function. The gauge functions are also very important concepts in convex analysis. I'm going to show you guys later. So the last example I'm going to talk about is minimum variance unbiased affine estimator. So if you consider a linear regression problem where we assume a Gaussian noise, and if you give me a matrix B, we are trying to look for an estimator for B transpose beta. We call it the estimator affine if it has this form, right? We call it unbiased if the expectation of this estimator equals B transpose beta. But just applying this definition, we have some constraint, right? We have AX equals B and C equals 0. So the minimum variance estimator on top of this is that we want to find the estimator that has the smallest variance. And, this reduces to the following optimization problem. So this basically represents the variance term. The reason why we have this is that you look at the variance of Z ahead, it translates to variance of Y. The variance of Y is sigma squared times V, but because we have X transpose in the front, so we get this trees of X transpose VX. So this is an example where we have a linear constraint where A and B are both non-zero, and we recover a GMF function. An interesting side note is that this formulation or this setup actually encapsulates a lot of special cases. For example, if you take V to be the identity matrix, we recover these very famous Gauss-Markov theorem in statistics. Okay, so let's start talking about this convex geometry of GMFs. So the key is to study the geometry of the set. It's the matrix-valued quadratic mappings. In particular, is closed and convex Hall. Right? So the reason is that previously we mentioned that support function has a correspondent with the closed convex Hall of this function. Right? And also once we have this, it also enables we do subdifferential calculus on these functions, which is what is more where the application needed the most. So back in 2015, Burke and Hoheisel, they obtained a representation, but in 2018, we obtained a much simpler representation, or we have a much better understanding of the set using a new class of cones, which I'm going to introduce next. So just to give you a brief brush on like what is a convex cone? A convex cone is just a convex set which is closed under a positive scalar multiplication. Right? So you can just pictorially think of it as a cone. A very famous example of convex cones is the positive semi-definite cone. So it contains all the positive semi-definite matrices. So we extended a little bit. So the KS, the class of cones KS is defined in terms of a subspace. So if we have a subspace Rn, so this set just represents all these symmetric matrices that are positive semi-definite with respect to the given subspace. And just because then the positive semi-definite cone is just a special case when we take the subspace to be the whole space. So we computed, in the paper, we computed the polar of the cone. So the polar of the cone is defined like this. It's all these points that forms a non-positive scalar or inner product with all the points in the original cone. So the formula for the polar cone is pretty intuitive, right? So it's just the cone, it's a conical of all this negative VV transpose for V in this subspace. And we see, so again, it's pretty intuitive to see why they have a negative, the inner product is non-positive. Okay, and based on this set of cones, we get this most very important theorem that the closed convex Hall of the set is actually given by the set omega AB. you see it in the form, it looks pretty much like the original set. We still have the linear constraint in there. And also take the special, oh, sorry. One thing I want to mention is that if whenever we write a matrix in the con, in the subscript, it actually means the subspace formed by the null space of A, because that's what we are going to be interested in. And take a special example. For example, we know that 0 is in the con, right? When we take 0 in here, we just recover the original set. Another important case is, for example, when A equals to 0, then the kernel of A is the whole space, right? So back here, we can see that when the subspace is the whole space, the polar con is just all the negative semi-definite matrices. And in that case, it sort of recovers our intuition about this hypograph, right? This is, again, this is the case when we have this the closed convex hull is the hypograph with respect to the positive semi-definite ordering. But with this linear constraint, AY equals to B, so this thing becomes K polar here. Just to give you some sense of the work we have been doing, so I just want to give you a proof sketch of how we are proving this theorem. So in order to prove equality, we usually just prove inclusion on both sides. First of all, we want to show that this omega itself is a closed and convex set, right? It is closed. The closeness is pretty obvious because we know the polar con is a closed set and all these mappings are linear, so it's closed. So to show that the set is convex, we just utilize the definition of a convex set. We take 2 points in the set and we show that a convex combination still lies within the set. So of course, it's easy to see that the linear constraint is easily satisfied because it's a convex combination. And the remaining thing to show is that we plug in the convex combination into this, and we show that the point still lies within K polar. And this is, so after some algebra, we can see it equals to this. And we know that by definition, this M1 and M2, they are in this K polar. The most critical thing is the thing in the front. Because we have both AY1 and AY2 equals to B, so we show that then we can see that Y1 minus Y2 actually lies in the kernel of A. And because we have this minus YY transpose this form, we clearly see that it lies within the kernel, it's a coin of this form, right? It lies within the kernel KS, K polar, right? So in that case, we show that this set is convex. And also because we just showed that 0 is also in the polar con, that implies that the closed convex hull of the set DAB is contained in the set omega AB, right? So to show the reverse direction is a little bit more involved. We basically use the Gauss-Markov theorem, which essentially says that if you know the dimension of a set, let's say the set lies in RD, we know that anything in the convex hull can be represented at most D plus 1 point in the set. So using the Gauss-Markov theorem, we are able to express anything that is in the convex set of DAB. Right? What we remains to do is that we do a constructive approach. We construct specific choices of these YIs so that it is equal to this omega AB. Right? Then we show the reverse inclusion as well. But I won't dive into too much details given the time. So after we have this closed and convex coins, this enable us to do the subdifferential calculus. We calculate the normal con and also subdifferential of the set, and also some other geometrical objects, for example, the relative interior. So as some special cases when we don't have the linear constraints, don't have the affine constraints, we can see the closed convex hull is just a very intuitive hypograph, and we have the interior of the set is equal to when we replace the semi-definite cone by definite cone. Okay, And we also studied the cases when b equals 0. As I mentioned, in that case, the function is a gauge. What is a gauge? So the gauge is also a function defined on a set. Essentially, it's the definition is here. It essentially represents how much you need to scale this origin set in order to reach the given point x. So we also give special treatment when b equals 0, when this function is a gauge. What is the support function, and what does the gauge look like? Okay, so now let's move on to the second part. In the second part, we study the infimal projection of the sum of the GMF function plus a proper closed convex function in V. So the objective is that we study the infimum projection in terms of the V variable. So that leaves us with a function in X. Right? So the idea is that a lot of the problems, right? So by different choices of the function H, we can explore the different structure in the matrix X. So it opens the door to some smoothing approach to solving this problem. This is most of the application we see that we are trying to optimize over a variable X of some loss function for X, plus some structure inducing penalties. Right? This is what we can get from GMF functions. So we establish conditions for the domain of P and under which condition P is closed and proper. We also give formulas for the commutation for the conjugate of P and subdifferential. We also give special explorations when, for example, H is a support function or indicator function. As an example, we recovered all weighted squared gauges on R and by M, and we have a complete characterization of variational gram functions, which I'm going to introduce to you later. So before I start to talk about the math or the results, let me first give you some of the examples, like how the specific choice of the function H and how it relates to the real applications. So for example, if we choose H as a support function, a special case of support function is just a linear functional, we can recover the nuclear norm of X. And for example, when we choose it as an indicator function of this set, the trace of V smaller than or equal to 1, we can recover the nuclear norm squared. So the nuclear norm is useful because it's a convex envelope of the rank function, and we talk about it's used as a penalty term to introduce sparsity in X. Just as a special case, for example, since the lasso problem, we have one norm here, could be rewritten as a minimization problem in both the variable X and V, but in this case, we have a GMF function here. We can later talk about the benefit of rewriting this problem in this form. Yeah, another thing is that the K-means clustering example we just talked about. In this case, this set of matrices Q we are actually minimizing over has a combinatorial nature because it has the assignment problem, right? So the matrix E itself has a combinatorial nature. But it's easy to show that under all these possible choices of assignments, we have this matrix Q, the trace is always equal to n minus k. With that, we can sort of relax this constraint a little bit. We augment the set to be the set R of all the matrices whose trace is smaller than or equal to n minus k. Then that allows us to get a lower bound on the objective K-means by applying the result before. And so next, I'm going to talk about these variational gram functions. So for a closed and convex set V in Sn, we define this omega V, omega subscript V as a support function of V intersect Sn plus, the positive semi-definite cone, of the function YY transpose. So this kind of functions are called variational gram functions. It actually can represent a lot of stuff, but the most importantly is it received some attention in machine learning because it has some orthogonality promoting properties. So to see this, take this example. Let's choose this. If you give me a matrix V bar, a symmetric non-negative matrix, I define the set of matrices as all the set of matrices whose element-wise the absolute value is smaller than V bar. And then if we walk through, because the support function, remember, is the supremum of a point and all these elements in the set. So when you calculate the supremum, depending on the sign of the inner product between yi and yj, you either would choose plus V bar or minus V bar, right? So the variational grand function actually reduces to this. So if you use this as a penalty function, you can see it introduces the orthogonal promoting properties. So what we show in this work is that all these variational grand functions are just conjugate of P. When we choose H to be an indicator function and A and B equals to 0. So it's just a special case. And as a result of that, we get a lot of the results on variational grand functions easily. For example, they're conjugate, they're subdifferential, things like that. Another closely related example is the Keefe PK norm. So it's defined as a generalization of a lot of norms, actually. It's defined in terms of the singular values. For example, as a special case, we have the Keefe norm is a generalization of the Schatten norms, which is in turn also a generalization of the nuclear norm. And the usual Keefe norm is called Keefe. The standard Keefe K norm is just the standard, the Keefe 1K norm. So we established a connection between the Keefe PK norm and variational grand functions, or equivalently the conjugate of P. Okay, so then let's, I don't want to spend too much time diving into the study of the in vivo projections, but I want to give you some idea, like what are the results we have been doing, right? So first is that we studied the domain of P, which is pretty important because we want the domain of P to be as flexible as possible, because usually in optimization, we want these parameter space to be as large as possible for us to optimize for. We give examples where the domain of P might not be relatively open, and in the case when B is not equal to 0. But I will skip this example, I think. So we also studied the conjugate of this psi function, which is the sum of these functions, which we can use to derive the conjugate of P. We also give conditions under which we call this condition the conjugate constraint qualifications. We give some constraint qualifications on this problem itself. So, okay, so these are the formulas we give for the conjugate. We also embed the problem P itself into a perturbation duality framework. That allows us to give a lot of more interesting results on the constraint qualifications. So let me skip this. Yeah, so we give a bunch of constraint qualification conditions. We know like under exactly which conditions the function have what kind of property. For example, we know when P is closed, when we have the zero duality gap, etc. And yeah, then that allows us to calculate the subdifferential of P, which is probably the most important stuff in applications. We also study the special case when the H is a support function. And through that, we also introduce some interesting concepts along the way, like what coin-compatible gauges, which I think I'm going to skip. As some specific choices, for example, when H is a support function, we, as a special case, when we choose as a linear functional, we get a bunch of different choices of semi-norms and norms. And when we choose h as an indicator function, we get the variational gram function. We also recovered all the possible squared gauges. And we also show that variational gram functions and their conjugate are actually squared gauges, which also a very interesting result. Okay, so I think I'm going to conclude. So, so basically we show that GMFs, they generalize the matrix fractional functions and they unify a wide range of applications. So in the study of GMFs, we know that the geometry of this set is central to the understanding. And now we have a pretty good understanding of this set. So most of the applications arise when we study the partial infemal projection of this form. The sum of the GMF and a function, closed and convex function in V. And this is usually used as structural inducing penalties in X. So we give all these constraint qualifications, these convex conjugate and subdifferentials through different choices of the function H, we obtain various kinds of results. So in the last part, I actually want to spend a little bit of time to talk about future work because many matrix optimization problems take this form, right? So the F can be thought of as a primary objective and P usually as a penalty, right? So this allows us to, the study allows us to rewrite this problem as a problem in this form where it involves a function, right? And it gives us a basis of exploring a wide range of numerical methods based on this GMF function. Because the benefit of writing this problem in this form is that we now have the subdifferential of the GMF function. We also know under which condition this function is differentiable. Right? So it can be used as sort of a smoother to this original problem. So I will give a very simple demonstration at the end using just the lasso problem. Right? So consider the lasso problem. As we said, it could be rewritten in this form, and just writing the GMF function explicitly in this form. We know that this objective is infinitely differentiable in this domain, right? When V is positive definite. For example, in this case, one can introduce constraint like this. We add an extra constraint that we enforce V to lie within this region so that it's always in the differentiable region. And we can solve this problem iteratively using Newton's method because we already give formula for the gradient and you can easily derive Hessian based on that. And as we let this epsilon gradually goes down to 0, we recover the original problem, right? So this results basically in a path-following algorithm for solving the lasso. But maybe that is not the most important applications because we could easily smooth the original problem in different ways, in other ways. But it just is a demonstration that what we can do using this theory we have derived. For example, because think about this multitask learning problem we described before. This can also be smoothed in similar ways. Okay, so so all the things I talk about, you can find it in these 3 papers. And now I think I'm open to questions. So any questions from the public?
Oh, you need to unmute if you were muted to ask a question.
Oh, did I mute anybody? Let me see.
Okay, so for example, you say you can do this with smoothing. There's one thing maybe you didn't point out is that this generalized variational gram function, the domain, what do you know about its domain?
The generalized matrix fractional functions. Oh, the domain. Oh, because we look at Oh yes, that's something I didn't mention in the slides. Yeah, we know that when the domain is it's not a closed set, but we know that for example, in a special case when a as b equals 0, we know that the function is differentiable in the interior of its domain. So the interior of the domain is this in this special case.
Okay, so it's continuously differentiable in the interior. And in general, what can you say about the domain? Does it have interior or?
In general, we calculated the interior of the domain, right? I think I put it somewhere. I didn't spend much time on the slide.
Right, so that's a fact that's true in general, that this function always has interior to its domain, domain convex, and it's continuously differentiable on its domain. But in fact, more than just differentiable, it's analytic.
So I'm curious if we just, I guess I was holding more questions for the closed session, but maybe it'll spur more questions if you go back to that lasso example at the end, just wondering, so in the lasso relaxation, the matrix V is not necessarily even symmetric. Is that right?
Oh, it is a symmetric matrix.
Okay. So it's a symmetric matrix. So just thinking about how to play with it. One issue is that you're going from a high dimensional vector X to a square matrix of the same form. Can you let V be represented by low rank, say, in principle, like LL transpose or something like this in this kind of path following idea?
Yeah, I think that's one way to do it. I think that's possible. Right? We can use some low rank representations for V.
So in fact, Sasha, I think you know of this work. It was done at IBM, where there's a way to do this path following with low rank representations of V. It's that work.
Okay. And then one other question.
That work wasn't applied in this context, but you can apply it in many contexts using those tricks.
I see. And one other question with this is, what happens if you partially minimize in X, this representation that you have? Do you get anything interesting?
We can write down the first order optimality condition for this, right? If you do partially minimization in X, you mean like doing it in an alternating fashion?
Well, I'm just curious if if something comes out, because if you do other types of smoothing, sometimes if you partially minimize, something interesting comes out and you learn what you've replaced the X with. It's like you pass entirely to the V problem, and then there's just something curious can come out, but I don't immediately see it. I was wondering if you had any fun things to say.
I think we can do that, right? Because the minimization in X is pretty straightforward. But then, let me see. Then the problem in V becomes a little bit more complicated. Yeah, I can't tell if there's any benefit.
Well, it helps in the factorization of V's that you want to use, because basically it's DD transpose plus lambda V inverse, because we're requiring the inverse of lambda, V inverse. So you can see that the inverse is picking out because it's lambda V inverse, it's picking out the active indices in X. Yeah. So the answer is yes, yeah.
Cool. All right, maybe I'll hold other questions until closed session. Maybe other people have more in the audience.
Okay, well, let me see, I can't regulate the screen very well, so I can't really, oh, there everybody is. Okay, so Well, if there's no further questions, Anne, do you have any?
Well, has this led to the development of new software, or is it mainly a theoretical analysis, or?
Yeah, so most of the work we have been doing is pretty theoretical, but it can lead to some future work on these numerical algorithms. Yeah, but we haven't have the time to explore that yet.
I see. Okay.
Yeah. Well, so perhaps we can move to closed session now.
Okay.
So just the committee members.
Wait, but is it, do you want to do more questions for, are you leaving?
Oh, sorry, are there any other non-committee member questions?
Okay.
So far, there's only been committee member questions anyways. Okay, so let's move to committee member questions. So those are not on the committee. If you would.
Thanks for coming.
Yeah, thank you for coming.